Hello. Well, this slide is obviously meant to be done in class because we can't really count how many of you are wearing white shirts unless we did a poll. And I don't know about you, but I'm just not really into that much work right now. So, how many students are wearing a white shirt? Let's say that there are 10 students wearing a white shirt. And if we had, how many students did we have? Let's just say we had 30 students total. I want you to please calculate what that percentage is. So, take out your calculators. You should have them anyway, right? It's no different than being in class. And how do we figure out a percentage? So percent means what? Out of 100. So we take 10 divided by 30 times 100. So 10 divided by 30 times 100 gives us 33 and 3 repeating. So 33.3% of students would be wearing white in this case. So that's percent. Percent composition in chemistry can actually tell us a little bit about the chemical and the compound, and those little tiny numbers at the bottom of a formula, P4O10, these are mole ratios, right? They are ratios of these compounds together. So they could also be mass ratios that we will find out that we can use the mass to get to these ratios of moles by using the molar mass. Well, actually, it doesn't have to be molar mass. It can be the formula mass as well. So the molar mass or the formula mass are the same number, right? We'll go through that. So we can use those to get to these mole ratios, and we can figure out what those numbers are. So that's exciting. And I know you're very excited. I can see it on your faces. Yes, I can see you. No, I can't. I'm just kidding. All right. So divide the total mass of each element. So how much of each element, we put that on the top, by the whole mass of the compound. That's the bottom. So numerator, denominator, and then you multiply by 100. Easy peasy, right? Percent composition. You're going to do that for each element and figure out what the percentage is for each element within a compound. So if we're given a name, we can determine the formula and we can come up with percent composition. So let's try it. So this is just another slide to tell us how to do it. It's just a little gray box with the formula in it. So it was on the last slide twice and it's on this slide once, and it tells you all the that you need to know, so you can pause it and come back to this if you need to. But let's do some. So what is the percent composition of iron 3 oxide? Well, the first thing we need to know is, what is iron 3 oxide? What is the formula? So the element for iron, and this is iron 3, so iron 3 plus, and oxide is O2 minus. So what is the formula? I hope you all said Fe2O3. I know you did. So just like in the beginning, we need to take each piece. We're going to take 2 times the mass of iron. And if you don't have a periodic table handy, you should grab one. So for iron, we have 55.85. You can do grams per mole or AMU. It doesn't matter. The units are going to cancel. So let's just stick with grams per mole, because then you guys can use grams per mole later on, and I'll be happy with that. So 2 times 55.85 is 111.7 grams per mole. This is for iron. Now for oxygen, we have 3 times 16. So 3 times 16 is what? Come on, do it in your calculator or do it in your head even. It's 48, right? You got this. Right, you don't have to do it in your head. You're allowed a calculator. We're going to add these together, 111.7 plus 48, and we get 159.7. To figure out percent composition, we're going to say for iron, we have how much iron? 111.7 grams per mole. divided by the total, which is 159.7 grams per mole. So this is where it doesn't matter what unit you use because it's going to cancel anyway. So 111.7 divided by 159.7 times 100 is, let me try that again, 111.7 divided by 159.7 times 100. That looks better. What, 69.94364433%. And for oxygen, we have 48 grams per mole divided by 159.7 grams per mole. Again, or AMU. Most of the time people use AMU for this. It doesn't matter. They're equivalent, so it doesn't matter. 48 divided by 159.7 times 100. When I click through in the PowerPoint, because I have a lot of these done in the PowerPoint, you'll see that I used AMU, but it doesn't matter. 5, 6, 3, 5, 5, 6, 7. So we have 69.9% iron. And for oxygen, we have 30.1%. There we go. Just like that. So please try this one. Oh, wait. I clicked through that. So there we go. So calculate the percent of each element in barium phosphate. So here's barium phosphate. I gave you the formula. I probably won't do that, or I don't have to do that because you know how to name things. And then this is the mass of barium phosphate. Now I gave that to you, but it doesn't really help because you got to go back and count, or calculate what is the mass of barium, what is the mass of phosphate and phosphorus, and what is the mass of oxygen in each of these anyway. So I'll pause this because I'm just going to click through these next two. I'm not going to write it out for you. All right, so the mass of barium would be 411. This is 3 times the mass of barium. Okay, gives you 411.9. And I can write that out if you want, but you have a periodic table, so each one is 137.3 if you'd like me to write that in there. Okay, so that gives you 68.44%. We can't subtract for 100 for the other two because we have phosphorus and oxygen. So next up being phosphorus, so we have how many phosphoruses? We have 1 times 2, so 2. Then each phosphorus has a mass of 30.97. So 30.97 times 2 gives us 61.94 for a mass of 68.44% barium. 10.29% phosphorus. You could subtract both of those numbers from 100, or you can just calculate out. You have enough of the stuff, so you can just say that the 8 times the mass of oxygen is 128. So this is 8 times 16, giving you 128, and that is the mass percent for oxygen. Good, I hope that went well for you. We have one more to try before we move on, so hopefully you're doing this. If you haven't done one yet, make sure you pause it here and try this one. This is the basis of where we're starting, and it's going to come back to this. So we want to make sure we have a good grasp on this. So pause it, and then we'll work through the answer. So we have how many carbon? We have 6 times 12.01, giving us 72.06. So this is equal to 72.06. So that is what this is divided by 180.16 gives us 40% carbon. Then our hydrogen we take 12 times 1.008, which is equal to 12.096 grams per mole, so we could do that divided by 180.16 and we get 6.714% hydrogen. And then for the oxygen, we have 6 times 16, or what is this equal to? 96. So you could take 96 divided by 180.16 and get 53.29% oxygen. So these would be your answers for this mass percent. And this is data that we can actually take this data and come back and we can find out information about a compound. So we can say, okay, this is a pure compound or an impure compound. And by taking this mass percent, we can take this data and find an empirical formula. And we're going to talk about what that is on the next slide. So an empirical formula is the simplest whole number ratio of all of the atoms in a formula. So something like C6H6 is not. I'm actually going to go back there. So an empirical formula is the simplest whole number ratio of atoms in a formula. Well, what that means is I could have C2H4. It's a very simplistic formula. There's only two elements, but this is not an empirical formula because I can divide both of these by 2 and get CH2. But something like H2O, I can't divide those, but something like peroxide, I can divide both of these by 2, so this is not an empirical formula. The empirical formula would be HO or OH. So the molecular formula then is the true formula. So this would be the empirical formula. The C2H4 in this case would be the molecular formula. So for water, H2O, this is the empirical formula and the molecular formula. They're the same. But for peroxide, this would be H2O2 would be the molecular formula. This is the empirical formula. So they are different sometimes, and sometimes they're the same. But empirical formulas from percent composition, it's a good analysis tool for us and allows us to think and look about things about the compound. So first we have to determine what is an empirical formula and what is not. So please pause the video and go through these formulas and try to determine if they are empirical or if they are molecular. Or you can just say empirical or not. If they are empirical, write yes. If they are not empirical, write no. So C4H10 would not be an empirical formula because we can divide them by 2. So if we divide them by 2, we get C2H5. C2H6 looks like it could be because we can divide these, but remember this is a 1. So this is an empirical formula because we have even, even, odd. Anytime we have even numbers and odd numbers mixed together, we're going to have an empirical formula. C6H6, I can divide both of these by 6, so no, this is not an empirical formula. The empirical formula for C6H6, which is benzene, would be CH. Water, we actually went over on the previous slide, is an empirical formula. CCl4, because of course water we have 2 and we have a 1, even, odd. Here we have 1 and 4, so we have odd, even. This is an empirical formula. And C4H7 is also an empirical formula because we have even, odd. So we can't divide those out. Well, now that we understand what an empirical formula is, we're going to use that. We're going to find those given percent composition or mass data for the compound. So this is a 3-step process. I'm going to use different colors. So step one is going to be convert to moles. So given mass data or percent data, we can find moles. So we always want to be able to find moles. Step number 2, and I'm going to color code this too. Step number 2 is find the mole ratio. Divide all moles by the smallest number of moles. So you're looking at the numbers that you found in number 1, and you're going to divide by the smallest number of moles. And for some reason, this is the step people forget. So don't forget this step. Not that you should forget any steps, but don't forget this step. It's very important. All right, they're all very important, but that one definitely don't forget. Number 3 is not always required. But some numbers can be rounded and some cannot. And these are the numbers that are going to represent the subscripts. So what we need is whole numbers. Have you ever seen a subscript that wasn't a whole number? No, because that would be a nuclear equation where we're splitting an atom and we can't do that. So what we're doing in these is trying to find, let's see, E, X, A, Y. So we're trying to find out what are these subscripts in the empirical formula. So those need to be whole numbers. So when we're going through, and from step number 2, if the number is some number .0 something, 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 you can round down or just leave it alone. If the number is .9 something, 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 you can round up. However, number 0.1, number 0.2, number 0.3, you're getting a trend here, number 0.4, number 0.5, number 0.6, number 0.7, and number 0.8, these are not roundable. If you just round them, you'll get the wrong answer. So what you need to do instead is you're going to multiply through until you get to a whole number. Some of them are relatively easy. In fact, most of them are relatively easy. So I wrote some number, 0.24, looks kind of like a quarter, right? Or 0.25. And I wrote 0.24 because it can be close. So how do you get rid of a fraction? You multiply by the numerator. So you would multiply it by 4 to get a whole number. 0.33 is roughly 1/3, so we multiply by 3, and 0.5 is a half, so we multiply by 2 to get rid of the fraction. This is not always required because step number 2 sometimes results in all roundable numbers. All right, let's take a look at our first practice problem. So our first practice problem, step number 1 is in purple. So step number 1 is find moles. And again, we are looking for something, so let's take a look here. Find the empirical formula of a compound that contains 741 grams of lead, Pb, and 76 grams of oxygen. So we're looking for X and for Y here. So what we need to do first is find moles. .207 grams of lead for 1 mole of lead. And that gives you 3.58 moles. Then we have oxygen. She meant to put a colon there. So we have 76 grams of oxygen, and each of those has a mass of what? So in the past, we've talked about oxygen as part of the Brinkelhoff. And in this, we said that these are all diatomic. But they're only diatomic when they're found naturally occurring by themselves. They'll be connected to one another. So in this case, they're not found by themselves. This is in a compound with lead. We're trying to figure out what that number is. So it's not 2, or we can't say it's 2. It's just oxygen. So right now we're going to use the mass 16 and not 32 for this. So 1 mole of oxygen. So when we divide that, we get 4.75 moles of oxygen. Okay, now step number 2. Step number 2 is find the mole ratio by dividing by the smallest number of moles. So 3.58 or 4.75, which is the smallest? I hope you all said 3.58 because yes, that would be correct, is equal to 1 here. Is going to be equal to 1.33. So now step number 3. Step number 3 is multiply to get whole numbers. We said this one's not always required, but in this case, we have a 1, that's a whole number, but 0.33 is not a whole number, so we do need to multiply this through. Some of you can already see what we need to multiply this by, but others may not. You can always do trial and error. So what is 1.33 times 2? Is 2.66. That is not whole and it's not roundable, so we need to continue. What is it times 3? 3.99. 0.9 is roundable, so we can say that that is approximately 4. Now in math and in chemistry, whatever we do to one thing, we have to do to everything else in this case. So we need to multiply this one by 3 as well, and we get 3 times 1, which is 3. So this is equal to x, and this is equal to y, and then we write it in our formula, PB 304. And that's it. 3 steps. These 3 steps you want to get down because there's going to be more added to it. So we're going to add a couple of pre-steps in a few minutes. So let's try another one, or actually I would prefer you to, I have the solution on a couple different slides here. I would prefer if you could pause the video and try it on your own. Come on, click. Okay, so step number 1 here, we're going to do, I want you to pause it. So if you haven't paused it yet, please pause it. And remember, we're looking for FE, we're looking for the X, and O, we're looking for the Y. So those are what we're going to be looking for here. And starting with step number 1. So pause it, please. Try it on your own. Find moles. 13.51 grams of iron. Each iron has a mass of 55.85 grams for 1 mole. So that gives us, for that, 0.2419 moles of iron. Then we have 5.79 grams of oxygen. Each oxygen has a mass of 16 for 1 mole, or 0.3619 moles of oxygen. Step number 2 is going to be find the mole ratio by dividing by the smallest number of moles. So which is smallest, 0.2419 or 0.3619? 2419 is smaller. Yep, so this is equal to 1. And this is going to be equal to 1. Let me just do this on my calculator again real quick. 0.3619 divided by 0.2419 gives us 1.496. All right, so step number 3 then. Get whole numbers by multiplication. Again, not always required, but in this case, we have a 1 and a 1.496. This one cannot be rounded. So trial and error even would lead us to the right answer even the first time we do this. So we multiply this by 2 and get 2.992. 2.9 something 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 is roundable, so we can say that this is 3. We're not done though, because we multiplied this by 2, we have to multiply that one by 2. So times 2 gives us 2. And now we have Fe2O3. And that is our answer. That is the last one like that we have. Hopefully you got that down. There should be more practice in your book if you need it. But the next one we're going to do, I'm just going to click through the answers here. The next one we're going to do is actually going to start with percent composition data. So here we go with percent composition data. This is what we learned how to calculate in the beginning. So we have 62.8% chlorine, 31.9% carbon, and 5.3% hydrogen. The easiest thing to do, so the easiest way is to assume you have 100 grams. Because this is percent data, no matter what size sample you take, you will end up with the same result. But if you assume 100 grams, since percent means out of 100, you're going to get the same number. Because I would say, okay, well, 62.8%, to get rid of percent, I divide by 100. And then I divide by 100, the percent goes away, and then I multiply this by the 100 grams, and I get 62.8 grams. So no matter what I do, I'm going to end up, if I assume 100 grams, I'm going to get the same number, and it just becomes a lot easier. So we can just assume 100 grams a sample. We can drop the percent sign and put a grams there. So number 1, so step 1, find moles. Okay, 62.8 grams of chlorine. Each chlorine has a mass of 35.45 grams for 1 mole. So that gives us 1.77 moles of chlorine. We have 31.9 grams of carbon. 12.01 grams of carbon for 1 mole of carbon is 2.66 moles of carbon, and 5.30 grams of hydrogen. Each hydrogen has a mass of 1.008 grams for 1 mole. And that is 5.26 moles of hydrogen. Step number 2 is find the mole ratio. And we do that by dividing by the smallest number of moles. So the smallest number of moles here, 1.77, 2.66, or 5.26. We're going to divide by 1.77. That is the smallest. So 1.77, and I can put moles here to show you that they cancel. All right, so 1.77 divided by 1.77 is 1. 2.66 divided by 1.77 is 1.50, and 5.26 divided by 1.77 is 2.97. But this is roundable, so I can round this to 3. My suggestion is anything that's roundable, round it before you do step 3. Otherwise, you might round yourself out of a roundable number. Get whole numbers. So remember, we're looking for some chlorine compound, carbon compound, and a hydrogen compound. We're looking for those X, Y, and Z, those subscripts in the formula, so they have to be whole numbers. All right, so this one, multiply by 2, and I get 3, right? 1.50 times 2 is 3. You don't believe me? You can check it. So if I multiply this one by 2, I got to multiply everything else by 2. So I multiply this one by 2, and I get 6. So my formula would be Cl, X is 2, carbon is 3, and hydrogen is 6. I get asked a lot which way I should write this. Normally we write things that are least electronegative to the most electronegative. However, with carbon and hydrogen, we usually write C and then H. Just a customary thing to do. So C3H6, and then the more electronegative elements, so Cl2. But at this point, I don't care which way you write it, as long as you write it that way, like with the right subscripts. So you have options. So now we're going to take it one step further and learn how to go from this empirical formula. Remember, these are empirical formulas. So these are empirical formulas. We're going to learn to go from those. So now we're going to take it one step further and learn how to go from the empirical formula to the molecular formula, once we're given some of the information about the molecular formula. So if we have an empirical formula, remember how we got to an empirical formula. So a few slides back, when we were doing the is this an empirical formula or not, how did we get from a molecular formula to an empirical formula? So if we said C6H6 is not an empirical formula, how did we get to the empirical formula? We divide it by 6, right? So the empirical formula would be CH, and we did so by dividing by 6. So now we have the empirical formula, and we want to go back to the molecular formula. We need to know what we divided by so that we can multiply everything back by that number. And it's a very simple process, actually. We just take the ratio of the masses. And so we're going to have to give you the mass of the molecular formula. So there's a lot of words. Here we have the empirical formula. We can calculate the molecular formula. And we do so by taking the molar mass of the molecular compound, so the molecular mass, and we divide by the empirical formula mass. You must be given this. It has to be given or determined in a lab in some way. So on a test, you would have to be given that number. There's no other way to get it. Empirical formula of lactic acid is CH2O. So you could have figured this out, by doing what we just did, the three-step problem. But now you're given the molecular formula mass. So we're saying this is the empirical formula. This is the mass of the entire compound. All you have to do is calculate this mass. So calculate the mass of this, which if you add up 12.01 plus 16, which is what, 18.02 plus, sorry, that's more than that. That's 28.02 plus 2.016 for hydrogen. Essentially, you get 30.03 grams per mole. Now, again, you can use grams per mole or AMU. It'll come out to be the same. So if 90.08 divided by 30.03 gives us a 3, that means we're going to go back to the CH2O and we're going to multiply all the subscripts times 3. So when we do that, we get C3H6O3. And that would be our molecular formula. Pretty cool. Okay, so we're going to practice that, but we're going to practice it in a minute. I suggest you take a small break here, go get a drink of water, just take a lap around your house, living room, apartment, I don't know, office, wherever you're learning from. Go ahead and take a quick lap around and come back and look at this problem because this one has a few pre-steps. So I'll do the pre-steps in blue. We'll do this first one together and hopefully the next one. But first, let me describe this to you. So this is a combustion. So anytime that you have a fire, you and your friends get together, you know, back when you were allowed to have friends and meet up with people with a less than 6 foot distance, you could have a bonfire and you and your friends would enjoy it, you know, with water in a beverage cup, of course. And you were happy, you know, remember happy times? Well, this is what we're going to be talking about now. What was going on in this combustion of organic material? So we're going to be focusing on what are called hydrocarbons. So that'll be hydrogen and carbon, or we can also include oxygen. So we can actually have oxygen in these too. And if you remember from our combustion problems that we were talking about, the products are always CO2 and water. It's just how much of each of these is going to be produced. So we have a sample. This is a carbon, hydrogen, and possibly oxygen sample. And we're going to put it into a furnace. And this is our fuel. So our fire triangle, we need oxygen. So oxygen is going to come in. This oxygen is coming in externally. So we're adding it in. Well, we have fuel, we have oxygen, and the furnace is going to be our spark or our heat. That gives us a triangle, a fire triangle. This is a fire triangle. You need all three of those things to have a fire triangle. And so when we have a fire triangle, we can actually combust the sample and it will do what we want it to do here in this case. Now, if you don't want a fire, then that's why you take away one of those materials and then you get no fire. This is going to burn. The material that comes off, which is usually a gas, is going to travel through this filter here, and then it's going to go out here and it's going to have water be absorbed. Well, guess what? Water is one of our products. And then it's going to travel here to a CO2 absorber, and CO2 is going to be absorbed. From this, we can take the amount of water and we can convert this to hydrogen. And we can take the amount of CO2 and we can convert this carbon. Because if you remember way back when we talked about what these subscripts are, or if you look at step number 2 that we've been determining, we're finding a mole ratio, and those are our subscripts. So subscripts are a mole ratio that we can use, and I can say for every 1 mole of water, there are 2 moles of hydrogen. And for every 1 mole of CO2, I have 1 mole of carbon. So we can use that information. Let me erase a bunch of this stuff right now. Now notice I didn't say anything about oxygen in these final products. Let's take a look at maybe why I didn't talk about oxygen. So one of the biggest things that people say is, well, I could take this and I could find the amount of oxygen from each one, and then I could add them together, and that would be the total amount of oxygen, right? Wrong. Because we added this oxygen in externally. Remember, we can have a CHO compound plus O2, so we add in O2 to get to the CO2 and water. So since we don't know how much of this we added in externally, that's a question mark, we can't do that because some of this oxygen that we got out came from oxygen that was not in the sample originally. So instead, what we're going to do is we're going to find the mass of hydrogen. So we're going to use the mass of water to find the mass of hydrogen. And we're going to use the CO2 to find the mass of carbon. And then we're going to take these and we're going to subtract them from the original sample mass. Because the law of conservation of mass says that if I have an original sample with a certain mass, right? If it has mass X, I better have my products must also equal mass X, because mass can't be created nor destroyed. So that's what we're going to do in the beginning, is we're going to convert them. You're going to see I'm still color coding this, and I'm doing that for your benefit so you can see where you can save yourself a little bit of time. These problems do tend to be a little bit longer though, so that's why I told you to take a break. All right, moving on to the next slide. Combustion of 18.8 grams of a substance. This is the original sample mass. That's important, we're going to need that. Produced 27.6 grams of CO2 and 11.3 grams of water. So I'm going to say pre-step 1. Find mass of carbon and hydrogen in original sample. So we start with 27.6 grams of CO2. The molar mass of CO2 is 44.01 grams of CO2 for 1 mole. Now, some of you might have that stuck in your head like I do, or you can calculate that from the periodic table, right? So this is where we come with our mole conversion. 1 mole of CO2 has 1 mole of carbon. For every 1 CO2, we have 1 mole of carbon. Now, you know how I always say don't calculate till the end, but right now I want to take this number and I want to calculate this number. So 27.6 divided by 44.01 times 1 divided by 1 is 0.6271 moles of carbon. If you remember, step 1 before was find moles, you might know where I'm headed. Those moles of carbon, for each 1 mole of carbon, we have a mass of 12.01 grams of carbon. So we're going to take and multiply that by 12.01, and we get 7.532 grams of carbon that were in the original sample mass. Then we have 11.3 grams of water, 18.016 grams of water for 1 mole of water. Again, calculating that from the periodic table. For every 1 mole of water, you have 2 moles of hydrogen. 11.3 divided by 18.016 times 2 divided by 1, and I just need to do this real quick, is 1.254 moles of hydrogen. All right, and we're going to say for every 1 mole of hydrogen, you have 1.008 grams of hydrogen. So that gives us times 1.008, 1.264 grams of hydrogen. All right, so now we have the grams of hydrogen and the grams of carbon that were in the original sample mass. So we're going to do pre-step number 2. I'm going to do it up here because I'm going to run out of room there. Pre-step, okay, what did I just do? Step number 2, subtract mass of carbon and mass of hydrogen from original sample. So 18.8 grams minus 7.532 minus 1.264 grams. 18.8 minus 7.532 minus 1.264 is 10.004. So that is basically the end of our pre-steps. So that would be the end of our pre-step. So this is grams of oxygen in the original sample. So we can do step number 1 from the original. Find moles. Well, if you noticed, as I was going through, I actually calculated the moles for carbon and hydrogen. And I figured, well, I'm already doing this math. Why should I have to go backwards and find it again later? That seems silly. So I calculated them as I go. But if you didn't, you would just take this number and divide by the molar mass. You'd do the opposite of this step right here. Now I just need to do this for the oxygen, 16 grams of oxygen. Oh, that isn't right. This is DeVos. So now I just need to do this for the oxygen. So I take the 10.004 grams of oxygen that were in the original sample. I divide by the molar mass of oxygen, which is 16, and I get 10.004 divided by 16 is 0.62525 moles of oxygen. And I didn't really need all those sig figs, but that's okay. So we're going to need to keep those numbers, and we're going to move on to the next slide. So 0.6271, 1.254, and 0.6256. Trying to think how to keep it all on the same slide, but there's just not enough room. So I'm going to keep going here. So we have step number 2. And I'm just going to write those numbers down before I forget them. 0.6271 moles of carbon, 1.254 moles of hydrogen, and 0.6256 moles of oxygen. All right, so step 2 is find mole ratio. These are the same steps we had before, that's why they're color-coded. All right, I'm going to divide by the smallest number of moles. Everything else is the same now, just those 2 pre-steps that we have. All right, so what is the smallest number of moles, 0.6271 or 0.6256? I agree, 0.6256. So 0.6256 moles. So let's do that. 0.6271 divided by 0.6256 gives us 1.002. 1.254 divided by 0.6256 is 2.004, and we have 1 because it's divided by itself. Now step 3, get whole numbers, is not required here because this is roundable to 1, this is roundable to 2, and this is 1. So in fact, we don't need to do that. We would say, oh, this is carbon, this is hydrogen, and this is oxygen. We would say CH2O. Now the original problem, if you go all back to this slide, says determine the molecular formula given that the molar mass is approximately 180. So we can actually take this empirical formula and find the molecular formula because we're given that this is equal to approximately 180 grams per mole. So the empirical formula mass for this, if you remember, we just calculated a couple slides ago, was 30.03, or it's actually like 30.026. So 180 grams per mole divided by 30.03 grams per mole. So 180, ow, my finger went numb. 180 divided by 30.03 is 5.994. Now this number should always be roundable. If you don't get a roundable number here or something looks like less than 1, you probably did something wrong. So try to go back and make sure you didn't make a typo. We're going to multiply everything in here by 6. So we're going to multiply this all by 6. C1 times 6 is C6, 2 times 6 is H12, and O1 times 6 is O6, or glucose. Funny how glucose, which is broken down in your body for energy, has the same empirical formula as lactic acid, which is one of the byproducts of anaerobic respiration that gets left in your muscles when there's not enough glucose, or excuse me, there's not enough oxygen to process the glucose. I can talk. So interesting how they're related. All right, so if you feel comfortable, you should pause this. And even if you don't, I feel like you should write down the question, take a picture of it, whatever, and try to work through this problem. Go back in the video and try to see what we did for each step of the last problem because this is exactly the same type of problem. It just has smaller numbers. So do your best, try to get this one done on your own, and I'm going to go through it just like I did the last one. So pre-step number 1 is going to be find the mass of carbon and hydrogen in original sample. So let's start with carbon. All right, so combustion of this sample, 0.1005 grams. This is the original sample mass. And it's of menthol. You do not need to know that it's menthol. I just told you that. So don't let that mess you up. You don't need to know the formula of menthol or anything like that. Produced 0.2829 grams of carbon dioxide. This is for carbon. And 0.1159 grams of water. This is for hydrogen. So carbon, we start with 0.2829 grams of carbon. The molar mass of carbon is 44.01 grams of carbon dioxide for 1 mole of carbon dioxide. And I need to fix this right here. I meant to say carbon dioxide there. And I said and wrote carbon, so I apologize for that. So now we're in moles of CO2. We want to go to moles of carbon. 1 mole of CO2 yields 1 mole of carbon. So that will actually give us, we're going to take a look at this real quick. It is, all right, 0.2829 divided by 44.01 times 1 divided by 1 is, and I'm going to change this to purple because this is going to be our step 1 later, 0.006428. You know, I'm just going to double check that real quick because I feel like 0.2829 divided by 44.01. Right? Yep. Sounds good. This is moles of carbon. We need grams of carbon for this step, so 1 mole of carbon has a mass of 12.01 grams of carbon. That's where that happened. Okay. So this gives us 0.07720 grams of carbon. All right, hydrogen, starting with 0.1159 grams of water that were produced, we can figure out how much hydrogen was in that. There are 18.016 grams of water for every 1 mole of water. And every 1 mole of water contains 2 moles of hydrogen. So 0.1159 divided by 18.016 times 2 divided by 1 is, and I'm going to change it to purple, 0.01287 moles of hydrogen times 1 mole of hydrogen has a mass of 1.008 grams of hydrogen. So times 1.008 is 0.01297 grams of hydrogen. All right, so then pre-step number 2 is find the mass of oxygen by subtracting mass of carbon and mass of hydrogen from original sample mass. All right, so 0.1005 grams of original sample mass subtracting 0.07720 grams minus 0.01297 grams. Please be careful, those zeros are easy to drop. 0.1005 minus 0.07720 minus 0.01297. We get 0.01033 grams of oxygen in the original sample. And we have step number 1 done for hydrogen and for carbon. We need to do that for oxygen by dividing by 16 grams of oxygen for 1 mole. So we take the 0.01033 and divide by 16, and we get 6.456 times 10 to the negative 4th. Now, if we were to write that non-scientific, it would look 1, 2, 3, 6, 4, 5, 6. So there are 3 zeros here and only 2 zeros in that one. So when we go to look at which one is smaller, we're going to have oxygen being the smaller one. And these are moles of oxygen. All right, I'm going to try to remember those real quick. Actually, I have them written down. I'm going to go to the next slide. But yeah, I'll go to the next slide and I'll just write down because there's more space here. So we have carbon 0.006428 moles of carbon. Oxygen, oh, sorry, let's do hydrogen, just to keep it in the same order. No reason to change anything. Hydrogen is 0.012287 moles, and oxygen is 6.456 times 10 to the negative fourth moles of oxygen. Okay, so step number 2 is to divide by the smallest number of moles. That's a division sign. So which is the smallest number of moles? We said this one, 6.456 times 10 to the negative fourth. And we'll write the same thing, 6.456 times 10 to the negative fourth. So when we do that, we get, let's see, I like to actually store those numbers in my calculator sometimes. It makes it way easier than trying to type them all in all the time. So if I had the 6.456 times 10 to the negative fourth, on the left-hand side of my calculator, it says STO with an arrow. I would click that, and then I would click up top where it says X. My button actually says X, comma, T, E, and N, and you can change it to any alphanumeric character, but I just hit store as X, and then I use it as X instead of having to retype it every time because I don't like having typos. So 0.006428 divided by the 6.456 is 9.956. 9.9 is roundable, so this will be 10. And 0.01287 divided by X is 19.934, and that is roundable as well. So this would be roundable to 20. So good, we don't have to actually do step number 3. Step number 3 is not always required. So step 3 is not required here because these are all roundably whole numbers. So our formula comes out to be C10H20O1. Now, going back to the original question said, determine the empirical formula. So this is the empirical formula. And then determine the molecular formula. So the part 2, said determine molecular formula if the mass is 156. And that's back a couple slides. So we need the mass of the empirical formula. So 10 times 12.01, which is 120.1 plus 20 times 1.008, which is 20.16. And plus 16. So 156.26 is our empirical formula mass, and the mass that was given is 156. So 156 divided by 156.26, I'm going to guess is about 1, or 0.9983. So 1 meaning it's the same. So this is the empirical formula and the molecular formula. It's both. So that is the answer to part A and part B. And I can click through the solution if you want. I know it's behind the writing here, but on the next slide, just so you have a chance to see it if you really want it. All right, that is going to be it for this video. I will get back to you with the solution stoichiometry stuff. So we will see that coming up, but it won't be in the quest on Wednesday.